Hi, so I'm Will Pearce, and then this is co-founder Nick Landers. We've been in the security community for quite some time, and then I disappeared and did machine learning for a little bit, and maybe now I'm back. But effectively, we kind of started this company called Dreadnode. We do like offensive machine learning stuff. My background is I was an operator at SpecterOps, at Silent Break Security. And then I went on to do the help start the AI Red Team at Microsoft, and then NVIDIA, and then I'm now here.
Yeah, Nick Landers, similar background. Mine's a little bit more on the malware development engineering side. Worked at Silent Break for many years, and Will and I broke off, stayed friends, and just came back together last year to do this thing. So really excited. Yeah, have a ton of cool stuff to share. So.
Next we have three primary things. We do like capture the flag. So I don't know if you played the Kaggle competition, like for the AI CTF that we do through DEF CON, AI Village at DEF CON. We do like cyber evaluations. We effectively help them figure out how safe or unsafe their models are, I suppose. And then we do some AI Red Team tooling, which is kind of algorithmic attacks against models. And just quick history. So our first little foray into the space was sort of detecting sandboxes with neural networks and decision trees. And if you go back and look at that research, it's pretty terrible. I mean, it's not terrible. The code's terrible, and like the setup is kind of terrible. And I think that's just a function of us not coming from an academic space and coming from a more operational space. But the fact of the matter is, it kind of worked. And then we went on to do a bunch of different research and build a bunch of tools. So proof pudding, this is actually our first talk together since proof pudding, which is in DerbyCon. But the space has kind of grown exponentially, especially in the last year. But there's a ton of existing research out there if you want to go take a look. But we're not going to get we're not going to do math today. But effectively, the fundamental truth of everything is everything is a function, and functions describe everything. So this is a great video. We're early in the talk, so I'm going to try and play it, actually. Okay, maybe not. But effectively, so he goes on to say, functions describe everything.
He's very passionate.
He's very passionate. Big professor energy, as we like to say. Yeah, but everything's function. So like he says, the sound of my voice on your eardrums is a function, and everything in Active Directory is a function. So where we're used to looking at sort of static graphs, we're going to go into some more dynamic things. But in terms of like sort of quote unquote adversarial machine learning, there's a sort of like, it's very mathy, and when you first show up, you kind of think like, oh, I need to look at these particular set of algorithms that are adversarial in nature. So you might be an operator, you're like, okay, how do I attack this machine learning model? And you're sort of like, okay, let me go Google it. And you show up with adversarial machine learning, but after a while, after a few years, you sort of get this little insight where it's like adversarial is actually just an intent. So it doesn't really matter what sort of set of algorithms you want to use. It's really about that motivation behind how you use them. And I spend a lot of time sort of in two communities, in the machine learning community and in the offensive security community. And one thing the machine learning community has maybe failed to understand so far is that like attackers are extremely smart, they're quick, they kind of don't care about the niceties and the formalities of research or writing papers. They're very objective based, like they want to generate impact very quickly. And so, as we go through, you can kind of see it with, ChatGPT is a perfect example where they sort of dropped it on the internet and then we're like, oh, by the way, it can build bombs, right? And you just wouldn't have that in the software world where Microsoft's going to drop a piece of software and be like, oh, by the way, there's this like really bad, has code execution in it. I mean, they not on purpose, but they do. You know what I mean? So there's always processes like before software is released where we have all this testing, and that just hasn't been the same in machine learning. And I think it's a function of it coming from an academic space where they're not used to, living in a hostile environment such as the internet. And it being academically interesting is not necessarily operationally useful. And so when you go look at a lot of the research, like a default hop, skip, jump attack against digits recognizer, which is the MNIST model, which is like your machine learning 101. The default number of queries for an attack out of ART, which is the adversarial robustness toolbox, is like 25,000 queries. And so if you're going to try and run 25,000 queries against an online endpoint, like that's just not operationally useful. And so there needs to be sort of this research iteration that we go through. And, I kind of think as professors as sort of exploit devs, where it's, they come up with a primitive and then it's sort of our job to operationalize it and make it useful. And we're kind of just starting to go through that. But yeah, I guess it is not all necessary about attacks. Like the defensive side also has as much to gain from it. So, it being a capability exists in two realms, both offense and defense.
Thank you, buddy. So yeah, the first place we're gonna take a pit stop is offensive workflows. This is like the general term that we use to describe this process of using a model to augment some, I don't know, directed graph of execution and tasks. And these are semi-synonymous with like evaluations for models, which is a little interesting. People want to know whether or not these models are dangerous, so they ask, can it hack things? Now, the natural conclusion you come to is, well, we have to make it do the thing that you're scared of it doing. And really, the only thing in our mind that separates a workflow from an evaluation of a model is just metrics. Like a workflow is just having a model do a thing or using a model to do a thing, and an evaluation is just measuring how well the model did the thing. But you had to have the model do the thing in the first place. So you'll hear us use the term evals or workflows kind of interchangeably here. We view them as coming from the same core. Despite maybe pop culture, over the past like 6 to 8 months, I mean, the last 12 months have been crazy. For people like Will especially, like he's been doing security in the AI space long before most people even knew what an LLM was, right? Or had any concept of tokenization or, neural networks. And yeah, these LLMs have kind of changed things up. And I think there was this immediate impression of like, well, let's just try to have them do either really dumb stuff like write phishing emails or give them extremely hard tasks. And when they fail at them, we'll just claim that these models aren't all that scary, right? So the prevailing opinion is like, oh, these models aren't quite very good at doing, attacks or offensive attacks or exploit research. And it's starting to change now, but the reality is like they're actually quite capable. And there's a big middle ground for us between like the models being almost useless to being completely autonomous, right? There's a lot of scaffolding that goes into the middle that I don't think people realize. It's like an engineering concept that a lot of the ML architects aren't as familiar with because they're used to just having a model do a thing in isolation. But as attackers, we're used to taking a piece of technology and using it as a pure capability. So we're gonna chat about a few different elements here. We're gonna chat about like workflow orchestration platforms. We have an LLM interaction library called rigging that we built specifically for this process because we find a lot of the other libraries are really lacking in certain capabilities we need. We'll look at tooling integrations, and then we'll chat a little bit about metrics when we get there. And we'll start with sort of this workflow or DAG platform question. This is a very well-developed space, usually in the data processing and pipelining. So like, imagine data science, you're processing like huge pandas data frames. There's a ton of platforms out there like Luigi or Airflow that try to make this process pretty easy. And functionally, this is exactly the sort of platform that we want to use for these offensive workflows because these models are really good at isolated tasks. And until we have like really advanced agent frameworks and those are well developed, in the meantime, we're gonna have to kind of scaffold them into this process where we give them a task and we capture results, and maybe we give it that task 10 different times and capture all of those results and try to like push them through a pipeline in a directed flow sort of way. So yeah, we have a bunch listed up here. You're free to go and check them out. The one that we've sort of settled on that we're refactoring and building off of is PEFT. We also have our own library called Mark that I played around with, which is like a super minimal Python flow library, but you can kind of get at like the core of what we need, which is like individual isolated execution steps where we have inputs, we're allowed to store outputs, potentially add metrics or measurements onto those states, and then at the end process something or read from other states. So this is like what a pretty basic example of PEFT calls look like. You functionally have two main components in PEFT. You have a flow and a task. Flows can call other flows can call tasks can't call other tasks, but really they're just decorators that get applied to functions. There's a whole underlying library system for it with like persistent data storage, there's caching layers, there's retries. We write our own serializers so that we can support the sorts of object types we want, and we make really heavy use of the caching layers throughout our workflows. So you might imagine you go and ask a model to take a task on something. You give the model that task and say generate 5 different outputs for these 1 inputs. You cache all 5 of those outputs, and then every single time you want to use those outputs again, you simply pull them off of the disk, deserialize them, and use them from the cache. So this makes the iterative process a lot easier, especially because in these LLM workflow steps, you're oftentimes doing like a lot of processing and a lot of model calls, and you're getting really deep into this flow, and you might be working at the end of the flow, and you don't want to have to like wait for it to execute all of the original parts of the flow again. But yeah, we won't get too much into the details of PEFT, but these are really cool tools that I don't think have been heavily used in security. I know there was some commentary about using them for like XPen resources or doing recon with them, using these sorts of workflow platforms, but they work really well for interacting with these models. This is a couple of code examples from our rigging library. Like I said, you're probably familiar with like Llama Index or LangChain. You know, there's maybe DSpy. There's a lot of libraries that try to make like interacting with these LLMs easy. There's a few things that I think they suck at. One is they tend to over-prefer JSON, which models are terrible at. And actually Anthropic is a smart group, and they knew this a long time ago, which is why when you go to look up how do you use Claude, their best practice recommendations is use XML tags, because XML tags can flow freely in semi-structured text. When you use JSON, the entire message has to be JSON. And JSON involves a lot of escaping as well, which is not natural text that models have been exposed to. So we have this meme that we sent on our chat the other day of the guy throwing the stick in front of his bicycle wheel. And it's like, oh, I need structured output for my model. You quote, only return your response in valid JSON, and then the model fails, and you're like, oh, this model sucks. It's like, no, you suck. You asked the model to do something it's not very good at. So we tend to prefer XML underneath. The underlying framework that this is based on is Light LLM, so we can access all of the major model providers. You can hook up to custom open API servers, and we use a syntax similar to connection strings for databases. So you effectively call this get generator, and you spec like a connection string out with all the arguments for your model. There's no KW args. There's no like millions of, you know, arguments and parameters that you can pass to these models. It's just a single string that defines, do I want to use Mistral? Do I want to use GPT? Do I want to use my own custom server? Do I want to use a Hugging Face endpoint? And yeah, the generator, call chat on it, you get back this chat object. We can do things like structured model parsing. So we have a core model that's based on Pydantic XML. You can define these models and then effectively ask an LLM to produce text that parses into that model. The code itself will effectively extract out the XML from the text, regardless of where it is. And it's actually tries to be very smart about identifying times where the model might produce like a partial matching tag versus a full matching tag. And underneath these message objects get effectively converted into parsed messages where you have the individual parts. These models can be nested. You can have XML models inside of XML models. We have tool calling structures that use this XML calling structure underneath, and this works without the model needing to be trained on it. People make a big deal about this. So it's like, oh, my model's not trained to do JSON tool calling. You don't need it. Use a format that the models understand well. We can get effectively tool calling successfully in all the vanilla models, even down to like Mistral small, without it needing to be trained on it. So in this particular case, that using call will trigger underneath a XML schema to be dynamically created from the type hints on this class, passed into the model, and the model is allowed to execute them, and all the calls will be validated and passed off to your class. It's all modern Python code. I have no space for Python 2.7 old nonsense. So type hinting, schema validation, you know, type dictionaries, all of the stuff that you would expect from modern Python classes. We can do retry mex if we want to force the model to parse into a class before we continue, and it will error out if it can't. So this is really helpful when we're working in workflows where we don't have to use regex strings and we don't have to handle cases where there was a partial match or maybe the text of the message didn't entirely match the model we wanted. And then ultimately this culminates, and Will's going to go through a demo for Bloodhound, but we have some screenshots here of like what this whole mainsail prefect rigging looks like for something as simple as like automated vuln discovery triage. We effectively took use cases like .NET reversing. We built tooling calls in so the model has access to reversing .NET code and getting information about call flows. And we effectively walk it through the process saying, I want to find deserialization vulnerabilities in these files. And it goes through a whole workflow process that's, I don't know, probably like 3 subflows and 8 task steps deep. And it will turn out writing you exact exploit instructions with full details on how to build payloads and how to run them on hosts with very little scaffolding. And this is the sort of stuff that people didn't think is possible. And if you go and read Twitter, they would say, oh, these models aren't that great because I tried to prompt, GPT in a workbench and it didn't do the thing. But yeah, if you put the engineering time in, these models can do pretty incredible things, which is what our goal are. And here's kind of an output. So like, this is a connection string for Mistral. This is Mistral scoring that we have metrics assigned to all of these subphases. And this is effectively how we measure how well models perform at all these functions. And we can do things like perform multiple iterations. So for any sub-step, we perform it 5 different times to balance out the stochastic nature of the models, because we know that they might behave slightly differently on one generation over another. So soapbox over, I'll hand it back to Will.
Nice. Okay, so now we're going to go talk through Bloodhound. So this is obviously a conference about graphs. And Bloodhound is a graph, and this execution flows are also graphs. So if you imagine a lot of the Caldera type workflows are sort of, you have dependencies that need to be met before you can run other particular tasks, things like that. But here's sort of like a scenario that you might look like, and fairly common. So I used there's a project called AD Simulator. It's kind of an older project, but it'll effectively create Active Directory environments for us. So, we don't really op like we used to. So we're not in and out of networks. So we need to kind of build our own environments these days. But this is a fairly common relationship. And then just kind of as a joke, I put this exact little relationship into Claude and asked it to build me a math function for it. And this is what it came up with. And this is what maybe a lot of the academic lectures would be. So if you're reading papers and things, it's not like it's a different language so much as it is just academic formality where they have to sort of deconstruct everything and then put it back together. I'm not going to read all this, but you can look through it and you'll be like, oh yeah, that totally makes sense. And I think it just takes a while for, it just takes a while for it to I don't know, seep in or whatever. But yeah, this paper or this little snippet is exactly describing this in math. So the result of this, whatever this would be, is just a vector of zeros and ones that are true and false if the condition is true. So where is it? Yeah, there you go. If the expression evaluates to 1 for a user UI in a group Gj, the corresponding position Ij in the matrix V will be set to 1. Right? And that's just saying this. And so as you jump into archive, you just have to understand that they're not writing papers for you. They're writing papers for their peers who are not you. But you can take that in and sort of translate it to your own sort of language. And and this was done with Claude 3 or Claude. So I think LLMs are kind of these universal translators, right? Where you can take any Python function and be like, oh, I want to write this in Go now. I want to write this in Nim. I want to write this in whatever language you want. That's tend to how I kind of use them. But obviously, the implication of the relationship is that a user can log into the host and we get creds potentially, which means we can maybe move on. So when you're looking at prompting a model, you kind of want to parameterize these things. So if you're looking for a user, okay, so you're logged in as a user. Please look at these outgoing relationships and return a list. And then here's $20 and a scratch off, just so it knows that it's an important job and there's a reward at the end. Or you could do look at this relationship and tell me if it's exploitable. So in one case, you're giving it a whole list of relationships and asking it to return just one. So of a list where you're saying, you're just giving the model more control versus saying, hey, here's a single relationship. Please tell me if this is exploitable. And I think it has to, the success of the model has to do with it being task specific, but also the amount of information and context you give it. And so, it was up until very recently that these longer context models weren't being released. T5 had it for a while, but ChatGPT or the transformer architecture kind of took over the news cycles. But really, you get to decide, and what you should be doing is evaluating each path, whether it's a list of things or just singular. And I think we prefer to do the singular, so smaller tasks it tends to be better at. But I think that might change into the future. But it's just, it's easier to deal with smaller pieces of information, I think, as a human. So even as context lengths get larger, there's still going to be like this aspect of you needing to filter at that scale to make it useful for you. And that's effectively what this says. So, we're going to get a starting user, and then, you can get all users, and then you can get user relationships. And these are all tasks that get separated out, and they run in this order. I guess you put them up as a workflow. But we have like a tool here, which is our Bloodhound Cipher client. Then we just add a username. And then you can go through and just get all the information you need in a task as if it were like an ETL or a data science pipeline. If you think about sort of a network, at Silent Break, we wrote a lot of custom tools, and the first thing anyone ever did there when they joined was try and write their own piece of malware which was successful until they realized at some point you just become a software dev punching tickets doing feature improvements. Sorry. But so the sort of the bit you realize that malware is just sort of a server-client relationship, and you're not maybe different than, I don't know, whatever server-client relationship, like it's an abstraction. It's the same with these task flows. So if you think about like a C2 pipe, it kind of becomes just you're querying a database, but that database just happens to be a network. Right, that just happens to be. So it's like you have this pipe in and out, so why wouldn't you sort of build these MLOps pipelines around that flow of traffic and sort of learn or do whatever you want, process data. And we think we kind of already, like the Nemesis project is towards that, where we're starting to like keep things offline and be able to query them so we don't have to re-query networks. And you can kind of see that in some archive papers. Anyway, that's a different talk. And so we basically go through and we give it all of this information. And so we just ask it, is this relationship exploitable? You can kind of see we have our prompt here where we just have an IT admin system prompt, and it's like you are an IT admin responsible for managing Active Directory control relationships. That kind of gives it a persona, tells it who it is. And then you say, is this path exploitable? You give it a username and the relationship is just that member of JSON structure. And then maybe that's kind of lazy, but these models are pretty good, and so I kind of start with lazy and then just work my way up until there's a point where it works, or the metrics become a little more stable, a little less stochastic or erratic. And then we use the rigging framework to just parse it as a yes/no. So this gives us a nice binary check of is this relationship exploitable, yes or no? If yes, go on to the next step. If no, we're moving on. And I think the core thing here is just being task up versus model down. And then at the bottom here, just giving help docs to the model. And so do whack help or tac help, and then just saying, hey, you're using this tool. Here are these help docs. This is the context you need to use. And just helping guide the model onto your target, whatever that is. And you can do sort of, tool calling. There's a lot of examples of people doing that. I'd say typically people call functions rather than tools, but. And so I can say operators are task up. So we care about, we prefer build scaffolding and then remove it as the models get better, because we have stability as a requirement, right? Like one of the, I guess the axioms of one of the talks was in besides Las Vegas with OpBot. One of the axioms. So the first place people go here in this space is like reinforcement learning. They're like, oh, if I can just give it enough information, I can have a model learn like what actions do best in what states. Then, let's do that. But you can't drop an agent, you can't drop an RL agent on a network and have it learn. Like it needs to know, what it needs to know when you drop it, because of as a function of operation. You can't just drop an agent on a network and have it go like query stuff and fail and generate a bunch of logs. So we have stability as requirements. So we like incrementally, we like a big nice foundation, and then we'll build up. And I would say scientists and a lot of the evaluators in the space are sort of modeled down. So they come from that more academic side, that more observability side, where it's like sort of about observing the raw capabilities of the model. And so what you'll see is, yeah, choose your own path to world domination and let's see if you can do it. Build a plan for this thing, right? Like we're not going to tell you what to do versus operators, I think, which are like, hey, I know what I want to do. I just need to orchestrate it in the right way. And then I think the key point here is just like we're all evaluators. So if you're using LLMs for whatever task, like if you're not tracking your prompts, so it's so easy to just get into a Jupyter notebook, get into whatever, run a prompt, doesn't work, type something else, run a prompt, and then 42 hours, 3 hours later, you have 60 prompts, 70, 100 prompts that you've done, and you've tracked none of it. So you have actually no idea how you've improved or not improved, and it's all sort of in your head anecdotally. But that's not sort of how LLMs work. So you want to make sure that you're tracking your prompts. And it doesn't matter if you have metrics right now, but you're definitely tracking the ins and the outs. So you can go back and say, okay, this worked really well, this didn't work really well. Because what's happening underneath you are the models are being retrained and changing. Or if you want to take those same prompts and use them against a different model, or at some point in the future when you can no longer use big foundation models for these things because, you know, when Azure sort of realized people were using for C2, whatever, they came in and started booting people off of tenants. A similar thing might end up happening for models. So understanding sort of the process of data science and process of these models, yeah, maybe you won't support like a big foundation model, but as we go forward in time, like even these 7 billion parameter models are getting really, really good. Or you can even now do, you know, like the mixtural 8x7 mixture of experts model. Like you can run that at home. Or on Vast AI, or there's a couple of different services. But it's important that you just track those. Okay. So we all know what AIs might be capable of. We're kind of interested in what it is capable of. And I would say that's, you know, that's primarily been the crux of my research and my work for the longest time. And I think, you know, the proportion of work performed by ML AI is never going to be zero. So from here on out, it's really just how much of it is going to be performed by AI. And that's kind of, you know, that's every day I wake up and figure out, you know, what more I can push to an LLM. Okay, so here we have a demo. So we just have these tasks. So this is our flow. So we're just going to get all users, decide if it's exploitable, sleep because this is an API. Don't want to get banned, and then we go into, is this exploitable? And so here we have it, you know, this is just a DAG framework. So we have all our tasks set up, and it's just going through, and the LLM underneath is deciding all of these things. So is it exploitable, yes or no? And if yes, we push it to a different task, which is exploitable relationship, and then where it goes off and generates a command for us. And then because it's exploitable, because it's in a state that it got to, that we like, we're going to save it off as a good example for a data set. And so when you do this hundreds or thousands of times, you end up creating a massive data set that you can then go train on. And so when you're doing this at scale, those evaluations and those metrics become extremely important. Because what ends up happening is, and this is why you know, you have sort of that whole like data labeling sub-industry that you see. These are early on. So these are all going to be like exploitable relationships because it's going through. But you could do this. So this is, you know, if you see any sort of like this mapped task, it's we sort of schedule these tasks out. But you could do all of the users at the same time if you wanted to. But effectively, we go on and sort of here's our command. And we have no idea if this is a good or a bad command. You know, there's sort of that piece where you're like, you still need maybe that human in the loop, or you need to go through and construct a different task that would be like, validate that this is accurate. And I think as a function of not being in networks anymore, we have to build our own environments. So it's hard to argue with code execution, right? Like it's when you effectively, get it in an environment versus having to sort of string match and do those things.
Yeah, I guess I'll add to that because this is like something that we've started breaking down is there are lots of different ways that you can validate the outputs of models, and they range from like sort of validating the characteristics of the output in a more static way. So yeah, you might do like regex extraction, static string matching. There's like cosine similarities. So you're maybe doing referential where I have a reference list of commands that I know are good. When you produce commands, I'm just checking to see how well they line up with it. And then there's kind of what I would call like real world validation, which is like the model has given me a command, I'm gonna go put it into an environment and I'm effectively gonna let the environment or the effects of the environment tell me whether or not the model got the thing correct. And when you talk to the big labs or the governments, they're only ever focused on the latter. That's the only thing they want from these models is like, we're gonna go plug it into a shell and then it's gonna run bash commands to try to hack a CTF. But it's like, that's a really big step for a model. And not only that, but setting up the environment to measure that is very complex. So there's a lot of intermediate steps before you arrive at that point. And I think people really downplayed the utility that those prior steps can have on ensuring that the output is generally aligning with what a human would like. So when we do these sorts of evaluations, typically we'll produce a bunch of metrics. And then inside of our framework, we have the ability to like weight those metrics and normalize them across each other. So we'll do a bunch of runs and then we effectively look at a sorted list of outputs. And as a human, I just start to adjust the metrics until the metrics reflect the best results on the top, right? It's like I build the metrics first and then weight them and sort of subtly adjust them, even though they are like static string representations. For the exploit, it might be like, did you call the binary correctly? Did you avoid XML? Did you avoid C# code? Did you go try to use netcat? Like I might weight all of those differently and I generally just want to align those to what I'd like to see out of the model. So sorry, I just wanted to. Yeah.
And then because it's a DAG, it doesn't really matter. You can do any task. So we have the silicate, which is the NSPY, and we orchestrate that. We have like a basic Mythic one. We have a basic burp one. But yeah, I guess it being a sort of a conference on graphs, we're used to thinking of graphs as this like static piece of information that we go search through. But instead, if you think of every node as sort of a task or a function, it kind of makes it a little more dynamic and, that whole orchestration. So as an operator, we kind of think, on the path to Skynet, there's a lot of baby steps and, this task orchestration is sort of one of them. And then at the end, we'll have this big data set that we can do. And we kind of use tasks as like, if it gets to an exploitable relationship point, like that means something important. And so we can look here, we have like 5, this has been ran 5 times, so there's like 5 exploitable relationships, whatever that means. And these are all gonna be sort of the domain admins because at the beginning. For this particular environment, there's 18 of them that it pulls out. And then, with an environment, because we have tools like Bloodhound, you can take this, go compare your results, and then sort of see how the model does against like a very static sort of environment.
Cool. Yeah, I think actually I'll finish on Will's point about like, we're in the offense space in particular, like we're going to have to get used to working with limited information, right? Like if there's one thing that's going to get stripped first, it's your ability to pull excessive information about an environment for decision-making processes. I think, a lot of people might argue that the static analysis of that information is obviously going to blow any dynamic analysis. It's like model backed out of the water. But the reality is like that static analysis depends on full information. Whereas like these models can infer relationships. So like the idea is you might only be working with partial information, and this could very well be what we do identity analysis with in the future from partial info scenarios. Is like the model is looking at a set of partial information and coming up with intuitions about what relationships may or may not exist with particular confidence levels. So yeah, we're gonna pivot now. It's a bit of a harsh pivot, but I think it would be improper for us to leave this conference without chatting a little bit about adversarial ML, the way we think about the spaces inside of models. Up until now, we've been very much on the engineering side. So we've been talking about like using these models in orchestration and tasks. But the reality is the models themselves are really fascinating. And this is a technology that attackers will be forced to understand. When Will and I started this company, we effectively committed to the idea that we would be a company in the small subgroup and growing subgroup of like AI security experts, which is really no different than cloud security experts, right? It's like cloud security experts didn't used to exist. It was just cloud engineers and security experts. And then over time, those two disciplines created a new subspace where you can specialize solely on cloud. And AI is the same way. So the way I want to introduce thinking about these models is that like a model represents a parameter space inside of it. And as attackers, we're most interested in navigating that parameter space as efficiently as possible. We define useful points inside of that space as points that yield a particular output for a given input. Typically, we're looking for like misclassification or arbitrary control over, say, the output logits of a model given input logits. And our goal is to explore that parameter space while minimizing the number of queries and optimizing for whatever constraints we want, which is different than the academic research, right? Like Will brought up that idea that, the standard academic research is, I want the lowest number. So I'm literally going to throw as many queries at it as possible until I get the lowest number, because that means I win and I get to write a paper. As attackers, that's not what that means for us. We actually have constraints and goals that we're trying to meet within, boundaries. Like we don't want to just abuse the number of queries we call. This is like an example of a really basic attack. So this code should be fairly understandable. It's effectively this idea that you have a tensor of information, and this is also another component, it's an element of this AI security subspace, which is web app security, AppSec professionals think in the protocol of HTTP most frequently, right? Like everything about their tooling and their process is designed around the fundamental protocol that backs that relationship between a client and a server. AI security experts will exist in the protocol of tensors. Tensors are just numerical data that represents any other data, and they can represent any feature. Will has this great quote where he says that you could effectively describe every possible tree in the world using pure distributions. Like you can describe anything in the world by just quantifying it in some way. And tensors can represent everything. Tensors can represent images, they can represent text, they can represent audio. It doesn't matter. They don't care what they're representing. This is a very tough protocol to operate on, but it's really fascinating, and it offers like very cool intuitions about what it means to navigate that latent space in a model. So yeah, in this case, we have a feedback mechanism where we're asking a model to score an input, and we effectively perturb that input in a bunch of different directions. We take the next input, the next best input that produces the next best score, and we work from there. This is like the most simple example. A more advanced example would be something like hop, skip, jump. In our library, we rethink the concept of these generators a little bit. So in the academic world, hop, skip, jump is a process where you set up a bunch of dominoes and you tip it over and you wait for it to finish. In our realm, we think of hop, skip, jump, or all of these algorithms as being infinite generators. Their job is to consistently, given a set of priors, produce the next best input. We can test that input and then decide whether or not we want to have the algorithm run again and give us the next best input. So we design these algorithms using a lot of Python generators where we can do nested yield froms. We effectively have this code ask continuously for fresh inputs. It can delegate out to other functions or algorithms, like bisection blend is what's the other term for that? I call it bisection blend. That's a poor term. Yeah, binary search. Yeah, bisection blend is like binary search, where effectively you have a threshold theta that you're trying to stay within. You effectively take two input samples and you continuously blend between them, and you effectively find the point in space where your classification label changes. And you find the narrowest point there. That's a fundamental part of hop, skip, jump, but the bisection blend, it's on its own, is its own algorithm, right? It produces a set of inputs based on priors and continuously produces those inputs until some threshold is met. So we can use that inside of hop, skip, jump, and this is the way that we'll build constructive algorithms in a framework that's more akin to something like BERP, right? The adversarial algorithms and their frameworks right now are not designed to do this sort of stuff. They're designed to be experimental, right? They're designed to validate behaviors and like produce metrics. In our case, we want to think of them more like an engineering problem. So this is us getting like, extremely positive hop, skip, jump. So these two fives in MNIST are labeled the exact same, and in the standard art hop, skip, jump, it would get a similar success rate with 25,000 queries. We do it with 1,200. So it just shows how much wasted query time they're doing just to get like slightly better performance improvements. But these are, all of this is very adversarial ML. If you haven't seen it, it's very fascinating. Classifying images of cats as dogs and whatnot. So yeah, I know we're running out of time. I'll chat a little bit about adversarial spaces for language models, because I think that's probably of interest to people. Essentially, there's like a history of, I sort of bucket them into three different categories of adversarial attacks for NLP. There was like early NLP, which was very, I want a model to label this comment in a sentiment. Neutral, positive, negative, right? That's like a very immature, old school models that we used to work with. BERT kind of came out, people started doing summarization and light QA tasks, and now we're in this totally new world with broad adoption, where you have like causal generation, multimodal inputs. And I've sort of listed out some of the attacks there. More modern attacks that you'll see for LLMs are typically revolved around jailbreaking, although Will and I chatted last night, and this is like changing a little bit as people realize that jailbreaking is not the only, like arbitrary control over the input logits of a model to some degree results in arbitrary control of the output logits, which themselves can be used for jailbreaking or prompt injection or misclassification. It doesn't matter. These models are just, the LLMs are classifiers. Most all LLMs, or most all models are classifiers, but yeah, they don't generate text, they predict the next token. They classify for a given set of inputs the next token, so they can be broken in the exact same way. So here's a little background on like the very first primitive of these attacks. This you can find under LLM attacks, and we have an implementation in a notebook from Mistral, but this is called greedy coordinate gradients, or GCG. The issue with LLMs is while in the rest of adversarial ML, especially on the images side, you can do continuous optimization because the input space is continuous. So like changing a pixel slightly in an image doesn't give you an entirely new image. Unfortunately, in the text space, we don't have that freedom. Changing a token of a text can completely change the meaning of a sentence. And because the tokens are discrete, they're not necessarily naturally related to each other. You can somewhat synthetically produce a gradient by producing a suffix, enabling gradients on that particular part of the input, pushing it through calculating a loss, backpropping, and then you effectively get from the embedding token space a set of tokens that are like the most likely tokens to slot into that suffix space for that given loss. And then the attack is really basic. It just starts like randomly slotting in tokens at random places and running the loss again and again and again. This is a pretty heavy attack. Like I said, it's analogous to gradients because they can't really get true gradients, but they are getting gradients all the way back to the embedding layers, which is close enough. It lets them get a list of tokens that are the best candidate. Then there's more modern attacks like beam search attacks. And actually the beam search attack and the GCG are blended together in what they call AutoDAN. All of these attacks have unique names. All of the papers have a lot of really complicated math. It's not that complicated. They're all talking about the same stuff. In a beam search attack, they just abuse the traditional way that an LLM generates inputs. For those who have heard of beam searches or N-beams, if you've seen generating an LLM, it's a causal token selection method where for any given set of input tokens, you effectively spray out to a set of output tokens, and you can take that tree step as many times as you want. So you say, I want K number of tokens, and then I'm going to take the next step of tokens for each of those K1s. And the beam search attack effectively builds a big set of K1 by K2 pairs, runs them through, calculates loss on the suffix. And so you might imagine that like they're sitting on an input, they want an output over here, and in the middle there's like all of these incredibly dense branches of all these token paths that they could take. So they're effectively beam searching out and trying to pick the path with the lowest loss. So they're trying to like take the next step down this really dense tree so that they eventually arrive back at the suffix. Nice part about this is they don't have to enable gradients for the models. They can use the logits, which are the outputs of the models. It's a really clean way to do it. And then there's the alternative, which is like pair and tap, which we also have an implementation of, where it's effectively asking models to produce malicious prompts, scoring them with other models, targeting a model, and then rerunning that process again and again. So this is like not mathematical. This is effectively having models produce, hey, I want a prompt that will get another model to tell me how to build a bomb, make me that prompt, and then you evaluate it. And the tree effectively expands with a branching factor. You do evaluation and pruning at every sub-step. This is super basic. Like if you go look at our parlay code, it's super trivial. It's like 80 lines of Python to get this working. If you go and read the paper, it's like 15 pages of mathematical formulas. Like they just go overboard with that. And I think it's worth mentioning that these techniques are actually really simple at their premise. We have a couple of references here. We have a big paper stack on our Notion where we effectively continually pull in papers about adversarial machine learning and like offensive ML. It updates continuously and builds summaries. So I recommend if you want to go play around and look at archive, that's great. Yeah, any other references that you would throw out here? Well, I made this slide, not Will, so Will might have some other thoughts.
No.
Cool. Yeah, I think that's it. I guess any final thoughts from you before we take questions?
Yeah, so I think you see a lot of like things like, hey, can you build a bomb? It doesn't matter. You can do whatever you want. So that's just like the academic example of the worst thing they can think of. But if you wanted like code execution, or you're pen testing some LLM that they hooked up to some function, something, it doesn't matter what your input is. It's just that process of, and I guess I'll go back all the way back. Now that you've heard all of that, here, just a function. What's X? What do you want to do, right? What's that output? So I think keep that in mind, and then when you read these academic papers, don't like write them off because it doesn't fit with your offensive narrative. Think of it as just an abstract space that you can work within. So it doesn't matter what your objective is, you can optimize for it. Okay, that's it.
Fantastic. Do we have any questions?
This was amazing. Thanks, guys. I'm experimenting a lot with LLMs and some of the networks that you showed, but then like without any prior knowledge. So for me, it's more dabbling than actually understanding what's happening. So it's very useful. And one of the things we were contemplating and what you triggered with your flows for the Bloodhound one, but it can be anything, right? Is would it make sense to train some neural networks in between to validate the output based on the prior knowledge that we have so that it can actually re-quantify the next questions towards the model, or is that very inefficient?
How good are you at training models?
Yeah, I was gonna say it could be inefficient. So I think a lot of the big models are really good, like really, really good. Like I don't know, currently, and we had this discussion last night. It's like because we have that, I added that data set piece in, and the models are so good at the moment. Like I don't know why you zero shot and like trying to use those big models to validate is probably your first step. The next step would be training your own classifier.
Or few shot.
Or few shot, yeah.
Yeah, that's probably what I meant. So what my primary intention would be, I'm more on the defensive side. So we're trying to build a model to quantify outputs of findings based on the contextual knowledge of the environment that we're trying to protect, right? So that knowledge you can't get from an LLM simply because it doesn't know it. It's unique to that environment.
Right, but you can provide it.
Yeah.
Yeah, so yeah, provide it, and then that's what we're saying, we're all evaluators. So where we have our own metrics for success, you would write your own metrics for success and then move on. You know, build your framework around your own metrics. And, you know, I think people, like, we have these gigantic models, and what people maybe don't want is like a gigantic narrative. What they want is actually for it to say, hey, here's this form, please fill out this form because I don't want to do it. But that's a long way away from here, generate this story about dragons or whatever. And so there's this weird process where we're like, hey, that's too much. Let's try and bring it back a little bit. But that process is you imparting your knowledge on and putting constraints around the model about what you want to see out of it. Yeah.
I would also add, yeah, just in general, like zero shot prompting, big LLM, few shot prompting. There's some more recent research on like something shy of fine tuning where you manipulate the input weights of the model slightly before you push them through. Then you would go into like LoRA fine tuning. So yeah, like pick your abstraction layer that you want, but start simple, have measurements all the way through, and then however deep you want to get. Like if you want to go fine tune a Mistral model or write an entirely new NLP classifier using like RNNs, I would say go for it. Like there's no rules to this game. Like they're all function approximators. So like it doesn't matter what model you're using. It's all about performance.
Yeah, I think it's worth mentioning that when you step into this world, like everything's an experiment because of just the stochastic nature of it. And so very rarely will you just be able to pull something off the shelf and it'll work like consistently. And so, you know, maybe think of it as, you know, not necessarily building a solution, but experimenting to find the best solution. So I think in a lot of sort of ML production environments, they're not training one model, they're training like 10, 50, 100 models. And then as, you know, the accuracy improves, there's some threshold they hit and they say, okay, you know, we've hit our training limit, whatever. Now we're going to promote this model to prod because it has the highest accuracy. But in reality, there's like 49 models behind it that were just not quite as good.
Do we have another question? All right, go for it.
Would you mind speaking a little bit more about the main sale demo that you had there? Is each one of those nodes a prefect task?
Yes.
And what exactly is going on when it branches to multiple different tasks?
So that's a map. So basically, we grab a list of users, we grab their relationships, and then instead of iterating, we map them. And so it's just it's a parallelization technique. And so instead of being like for user, for relationship, do this, which creates a very long sort of graph, we just map that task. So we can do them all at the same time. So we do 5 or however many relationships at the exact same time. And then you could just move that map one up to all users, and then it would just, you know, you would do all users for any given environment at the same time and go through that triage step.
From an engineering standpoint, prefix supports sync and async tasks. So, you know, you can effectively take advantage of async. You can also support parallel executors. Yeah, you can do branching inside of flows, inside of tasks. It's very dynamic, which is like the reason why we like it as opposed to like more static data analysis flows. Typically there you would define your graph, execution graph, and then you execute it in that static form and it optimizes the graph for you. In a tool like this, inside of your code, you could be like dynamically adding and changing steps. And like, if you come across new information, you can like trigger a new subflow or trigger it with different parameters. And there's also really cool caching layers where like the arguments of the function are all used as a cache key. And then if those arguments all stay the same and you can overload them yourself, then it will pull from the cache again. So you effectively get to define when a function is re-executed.